All right, welcome everybody. Today we're going to talk about lesson number 36, which is all about solving both exponential and logarithmic equations. Now, we have already solved easier versions of these two types of equations earlier on in our discussion, but we're going to extend upon them today to solve more challenging problems. The thing that will allow us to do that is by examining the fact that exponential functions and log functions are inverses of each other. Now, if you think back to chapter 1, section 1.9 in particular, all the things that were true about a pair of inverses, and remember that inverses always means opposite, all the things that are true about a pair of inverses are still true graphically in terms of their equation, and we're going to examine those over the next couple of lessons. But today, we're going to use them mostly to solve, and first we're going to use them to simplify. So we have a couple more properties of logs. They don't have fancy names, but they're here in the left-hand boxes. So it turns out, using the idea that they are inverses, if you have log base b of an exponential of the same base b raised to a power, you can go ahead and use the property of inverses to essentially cancel that log and that base, which would just leave you with whatever is up in the exponent. That would also be true if you had an ln, which is base e, of e to the n. If you look underneath, if you had base b raised to the log base b of a, again, as long as you have the same base of both the exponential and the log, they essentially cancel out because they're inverses to just leave you with a. And similarly speaking, when it comes to the natural log relationship. So now that we understand that those are true because of inverses, you're going to go ahead and simplify the next 8 problems. Notice that the majority of these problems come in the form of variables in them, which means you would not be able to just plug them into the calculator. You'll also want to take special note of when there is and is not parentheses, because if there are parentheses, you don't want to change them. So starting with the ln of e to the 3x. If you have a ln, which of course is base e, and then you have an exponential, which is also base e, using the property of inverses, they essentially cancel, and you would just be left with whatever is up in the exponent, which would be 3x. For the next one, I would probably start by rewriting it as e to the 2/3 power. Then, once you have confirmed that you have an ln, which is base e, of an exponential, which is also base e, property of exponent says, or property of inverses says you can just go ahead and cancel them to be equal to 2/3. Now, while these properties are great and very handy, they only work precisely when you have exactly what is in those boxes. So 10 raised to the 2 log x, a little bit of a problem there. Big problem, actually, in the fact that there is that 2 there. So the fact that there is that 2 there, because it's in between the 10 and the log base 10, I can't use the property immediately. I have to first go back to a different log property, which says I can take that 2 and move it up to the exponent. Remember, that's the power property. So I can rewrite this as 10 to the log of x squared. And now that I have base 10 raised to a log base 10, now the inverse property applies, and I can safely say that that is equal to x squared. We have a similar issue in the next problem. That 2 out front can't be there, so I'm going to go ahead and move it up to the exponent, which would give me e raised to the ln of x plus 1 squared. Then, once you have base e raised to a natural log, which of course is also base e, those would essentially cancel, leaving you with just x plus 1 squared. I might let you leave that as your answer, but if I wanted you to FOIL it, you would do x squared plus 2x plus 1. Let's just go ahead and do that just to make sure that we can. Then let's go ahead and take a look at the next row. So e raised to the ln of x plus 2. Again, you have a e, you have an ln base e. Properties of inverses say those cancel to be x plus 2. Again, careful in the following example. So even though you do have an e raised to an ln of x, you also have that plus 2. You're not allowed to just kind of pick and choose when to use the properties. You have to get them exactly. So the only way that these properties can be used is if you take that e to the ln x plus 2, and if you break it up into e to the ln x times e to the 2. Now, of course, remember why you're allowed to do that. That's just using the properties of exponents. When you multiply exponents of the same base, you would add them, which means you can work in reverse. Once you've done that, over here, e raised to the ln base e, those would cancel to just give you an x. E squared cannot simplify, so your answer would just be x e squared. A similar situation happens next. You can't pick and choose just the properties that you like, so you're going to have to first rewrite this as 5 squared times 5 to the log base 5 of x. 5 squared, that is, of course, 25. 5 raised to the log base 5, those essentially cancel, which will leave you with just an x, which means your final answer would be a 25x. Then in the final example, you're actually using the property more than once. So over here, we have log, which is base 10, of an exponential, which is base 10, which means those are going to cancel to just give me 3x. Then we have a natural log, which is base e, of an e to the something. So they cancel out to just be the somethings, which would be 3x plus 3. Please don't set that equal to anything. Please don't divide by 3. Please just leave it as a quantity 3x plus 3. So using these two, again, very important rules of inverses is what allows us to not only simplify those 8 problems, but it also allows us to solve a variety of log and exponential equations. So if you take a look at the next set of problems, generally speaking, there are 2 types of exponential equations, or 2 classes of exponential equations that we are going to need to be able to solve, those of which can use like bases, which we've already done, and those of which cannot, which means you need to use their inverse, which would mean you need a log. So let's start by doing one of each. So over on the left-hand side, 3 plus 2 to the 3 minus 2x equals 11. Start off with just the algebra before you try to do any pre-calc. So you're going to go ahead and subtract 3 from both sides. That's going to give you 2 to the 3 minus 2x equals 8. Hopefully, now that we have spent a ton of time here on exponentials, you will clearly recognize that you can rewrite 8 as 2 to the third. So 2 to the 3 minus 2x equals 2 to the third. Once you have 2 to the something equaling 2 to the something, again, like bases or the 1-to-1 property, you can essentially get rid of those 2's and set the exponents equal. So subtract 3 from both sides, you're going to get negative 2x equals 0. If you divide by negative 2, you're going to get an answer of x equals 0, which the fact that it's 0, no problem on that. Very easy to check these types of problems. If you were to go back and plug the 0 in, you should in fact get the left-hand side equal to the right-hand side. Something else to be aware of here, notice that this is an exponential equation. When it comes to exponential equations, the domain of an exponential, remember, is all real numbers. So no matter what you get will be a solution. You don't have to worry about checking for, negatives and zeros. That's only for logs, not for exponentials. So then for number 2, notice that we would again start with the algebra, which means we would go ahead and add the 3, which would give us 5 to the 2x equals 12. And then we'd have a little bit of an issue. So obviously there is no like base to 5 and 12. Back earlier in the chapter, we would have used the graphing calculator. While technically that still is an option, we now have a better option, which is instead to use a log. So if you want to now solve using logarithms, whatever base is being raised to the exponent, so in this case, the 5, you're going to take log base, in this case 5, of both sides. So you're going to take log base 5 of 5 to the 2x equals log base 5 of 12. You're allowed to do that using properties of equality. What you do to one side, you do to the other. Here's where the good stuff happens. Because you took log base 5 of an exponential, which was also base 5, that's that property from earlier, which says that they essentially cancel, and you're just left with 2x. So 2x is equal to log base 5 of 12, which is almost what we're looking for. Because we're trying to solve for x, we're going to go ahead and divide by 2, and it looks a little cleaner if you write it as 1/2 log base 5 of 12. That is what we would call the exact solution, which I do want to see that you're able to do. And then I also want you to go ahead and find the decimal. Remember that if you're finding the decimal, you're going to round it to 3 places, but you also have to remember how to put that in your calculator. Remember that that is the change of base formula. You would have to do log 12 divided by log 5, or you can use that special log base button in your calculator that I showed you yesterday. Whatever that number happened to be, you would then have to multiply it by 1/2 or divide it by 2, and either way, you're going to get 0.772 as your solution. So again, please just make sure that you're aware going forward. I do want to see not only this, which again is what I call the exact solution, but I also want to see you round it as a decimal. That shows me that you not only know how to do all the algebra, but you also know how to use the calculator correctly. Both skills are important. So let's go ahead and do a couple more, keeping in mind that from this point forward, the types of problems will be all mixed up. On a test or quiz, you'll just be given a whole bunch of equations and asked to solve, which means you have to solve using the best and most efficient method. So for the next set of problems, it's the same thing. Solve each exponential equation and round to 3 decimal places if necessary. So always start with the algebra first. So the algebra in number 3 is just to divide by 3, which gives you e to the 2x plus 1 would be equal to 4. Clearly, there are no like bases for e and 4. So instead, you are going to take the log of both sides. Because of the fact that the e is attached to the exponent, you're going to take the natural log of both sides. So the natural log of e to the 2x plus 1 equals the natural log of 4. Again, ln base e of e to the something, that's the property of inverses, which means those cancel to just be 2x plus 1. From here, again, you're going to solve for x. So in order to solve for x, you would subtract the 1 plus ln 4, or you could say ln 4 minus 1. If you put the ln 4 first, you should use parentheses just to indicate that you know that the 4 stays where it is. And then you would divide by 2. Again, I skipped a couple steps there. Subtract the 1, divide by 2. I would want to see that as the exact answer. And then, of course, using the calculator, which would be a little bit easier, you would find the ln 4, use parentheses as needed, subtract the 1, then hit enter before you divide by 2, and you will hopefully get the answer rounded to 3 decimal places, which is 0.193. And I say again, I would want to see not only this here, which shows me that you know how to do all the algebra, but I would also want to see 0.193 to indicate that you know how to correctly use the calculator. In number 4, start with the algebra. So I'm going to go ahead and subtract 4, which would give me 2 to the 3 minus x would be equal to 6. Don't be fooled, 2 and 6, even though they do have common factors, they do not have common bases. So I'm going to have to log both sides because of the fact that the 2 is what is connected to the exponent is how I know that I'm going to take log base 2 of both sides. On the left-hand side, log base 2 of 2 to the something, they just cancel to be whatever the something is, which in this case is 3 minus x, and that is going to be equal to log base 2 of 6. Since my goal is to solve for positive x, I'm actually going to move my x to the right, which makes it positive, which means I'm going to leave the 3 on the left and then subtract over log base 2 of 6. So 3 minus log base 2 of 6, again, that is the exact answer. Carefully putting that in your calculator using the change of base formula and any parentheses would give you a decimal answer of 0.415. All right, so a couple more exponential equations here in number 5. Now, obviously, that looks quite a bit different, a little bit more complicated, but hopefully, if you look at it closely, it also looks somewhat familiar. It kind of looks like a quadratic, except instead of factoring with x's, you're going to be factoring with e to the x's. Now, because it's a 1 out front, that means you can factor it very similarly to how you would if it was a 1x squared. So you're going to set up 2 sets of parentheses. Instead of having x and x, you're going to have e to the x and e to the x. And remember, that would work because if you were to multiply those out, you would add the exponent, x plus x would be 2x. So that's why it's an e to the x for each. Then you would still need factors of -5 that add up to be -4. So that would be a -5 and a +1. Just like in the past, you have to then set each of these parentheses equal to 0 and then solve. So e to the x minus 5 is equal to 0. E to the x plus 1 is equal to 0, which means that e to the x equals 5 or e to the x equals -1. Now from here, because of the fact that these are base e's, you are going to take the log of both sides. And again, because these are base e and base e, you're going to take the natural log of both sides. So this will be the natural log of e to the x equals the natural log of 5. And then draw a little space here. The natural log of e to the x equals the natural log of -1. Over here on the right, ln base e of e to the something, that just becomes the something. So we can say with confidence that x is equal to the ln of 5. That is, of course, the exact solution, which if you were to plug it into your calculator, you would get 1.609. On the other side, ln base e of e to the x, that would just be x, and you would get x equals the ln of -1. Now, hopefully, that would alert you to the fact that you cannot take the log of 0, nor can you take the log of any negatives. So we would reject that solution, which would mean your only solution is exactly the ln of 5, or if you make it a decimal, 1.609. So just like in the past, you might have to potentially be rejecting solutions if it gives you the log of 0 or the log of a negative. Had you gotten both negative logs, then it would be no solution. But because of the fact that there is one, that is the answer. And then as hard as it's going to get in terms of exponential equations would be over here in number 6. So again, not only do we not have any like base for 2 and 5, but we also have exponents on both sides. So how do you know which log base to take if one of them is base 2 and one of them is base 5? Again, another solution method would be to use the graphing calculator, but this is all about logs, so we want to go ahead and make sure that we can do it that way. So when you come across an example like this, where you have two bases that there is no like base, and you have exponents on both sides, because you can't decide which log base to take, you're actually going to take the natural log. So you're going to take the natural log, the ln of the left side, and then you're going to take the natural log of the right side. Again, properties of equality, what you do to one side, you could go do to the other. And so now we're going to go back and use those log properties from the last lesson. The log property says that if there's an ln, you can take anything that's up in the exponent and you can actually move it down to the front. So my next step here is going to be bring down the x plus 2 times the ln of 2. And then on the right side, bring down the x minus 3 times the ln of 5. Then from here, you're going to distribute. So x times the ln of 2 plus 2 times the ln of 2 is equal to x times the ln of 5 minus 3 times the ln of 5. Again, keep in mind here that your mission is to solve for x. So if you're trying to solve for x, you should start by getting all the x's on one side. So x ln 2 minus x ln 5 is going to be equal to -3 ln 5 minus 2 ln 2. I know it doesn't seem like we're getting closer to the answer, but I promise that we are. Because of the fact that you have x's in both of these terms, in order to get the x all by itself, you would have to factor it out. So factor out the x, which would give you ln 2 minus ln 5 equals -3 ln 5 minus 2 ln 2. And in your final answer, to get the x all by itself, you're going to have to divide the right side, which is -3 ln 5 minus 2 ln 2, all divided by the ln 2 minus the ln 5. And believe it or not, that is the answer. And again, that's the exact answer, which more than likely would be acceptable. But if you were going to go ahead and calculate the decimal approximation, make sure you do the entire numerator, hit enter, then divide by the entire denominator, which you'd put in parentheses, and that would give you a final answer of 6.782. And again, make sure that you round that to exactly 3 decimal places. So certainly it escalated there. These are good representative samples of the different types of exponential equations that you will have to solve. And remember, those that can be solved with like bases, you're going to see those mixed in as well. Just like there were 2 different classes of exponential equations, there are also 2 different classes or 2 different types of logarithmic equations, one of which we've already seen, and then one of which is a little bit new. So here in number 1, this is an example of one that we've seen. We have all ln of 8s. So over on the right, we're going to start by taking those natural logs of the same base, and we're going to go ahead and use the addition property, which says I can take those logs that are being added and turn it into multiplication. Then remember, that's what I like to call like logs. If you have ln of something is equal to ln of something, you can confidently say that those somethings must be equal. Again, that's a quadratic. We like our quadratics that are equal to 0. Factors of -8 that add up to be +2 would be +4 and -2. That means that your, again, potential answers are -4 and 2. Remember, in order to confirm whether they are or are not answers, you'd have to go back to the original, and everywhere there's an x, you would have to plug in those values to ensure that you don't get the log of 0 or a negative. If you plug in 2, you're good to go. If you plug in -4, that gets rejected. So 2 is your only answer. Again, keeping in mind that it could be no solution if neither of them worked. And then the other class of log equations would be over here on number 2. Notice right from the start, you only have a log on one side as opposed to the other. So that's your big clue that you have to use this particular solution method. Always do any algebra first. So I'm going to start by just dividing by 5. So log base 4 of x minus 6 would be equal to 3. And then you need to somehow take this log equation and turn it into an exponential equation. We're going to be able to do that using rules of inverses. A few minutes ago, in order to take an exponential and turn it into a log, we took the log of both sides. Now that we have a log, we're gonna go ahead and exponentiate both sides. So in order to exponentiate, whatever the base of the log is, that's how you know what base to use for your exponent. So you're basically gonna exponentiate the left side. 4 to that equals 4 to the third. So by raising both as a power, we call that exponentiating. So I'm going to exponentiate both sides using base 4. Now over here on the right, so 4 raised to the log base 4 of something. Again, that very first rule I showed you, those 4 and the log base 4 cancel to give you x minus 6. 4 to the third is on the right. 4 to the third is equal to 64. And if you add the 6, you're going to go ahead and get an answer of 7. Okay, and now that we've reviewed the 2 different classes of log equation types, let's go ahead and make sure that we can solve them when they're all mixed up. So in number 3, notice that even though we don't have logs on both sides, we do have multiple logs on the same side, which means we should first put them together using the log properties. So we're going to go ahead and take that subtraction and turn it into a division. So log base 2 of x plus 2 over x minus 1 equals 3. So then, because we only have logs on one side, and because of the fact that it's log base 2, remember we're going to exponentiate both sides. So we're going to make it 2 raised to the left side equals 2 raised to the right side. So on the left side, 2 raised to the log base 2, that will cancel to just be x plus 2 over x minus 1. 2 to the third on the right side, that's going to be equal to 8. Technically, that's 8 over 1. So I'm going to cross multiply and get x plus 2 equals 8x minus 8. If I put all my x's on one side, I get 7 of them. Constant on the other, I get 10. So x potentially, again, potentially only, equals 10 over 7. In order to confirm that that does work, I would have to go back to the original. Everywhere there's an x, I would have to make sure that it doesn't give me 0 or a negative. So 10 sevenths plus 2 is safe. And 10 sevenths minus 7 sevenths is also safe, which means my answer is exactly 10 over 7. And again, I think that's an example of one you would certainly leave, but if you wanted to round it to 3 decimal places, by all means. Notice in number 4, we actually have ln's on both sides. So this is what we saw a few lessons ago, whereas if you have like logs on both sides, you can essentially just set them equal. Just to be clear, if you don't want to remember 2 different techniques, you could solve number 4 exactly the same way you solved number 3 by exponentiating both sides. Because these are ln's, you would exponentiate both sides by raising both sides e to the side. So on the left side, e to the ln base e, that would cancel to just be x plus 3. And on the right side, e to the ln base e would cancel to just be 2. So if you just recognize right from the start that they're equal, you can just go ahead and set them equal right from the start. But if you want to show the process, by all means. So x potentially equals -1. If you go back to the only variable in the original, -1 plus 3, that yields a positive number, which means even though you got a negative solution, it still is an answer. So don't try to just use a shortcut by always eliminating the negative, because that's not always the case. Finishing up with something like number 5 and 6. So in number 5, the left side, we're going to go ahead and use the addition property, and we're going to multiply. So log of x squared plus 3x equals log of 10. Remember, at this point, since they're both logs, you can just get rid of the logs, or if you want to exponentiate both sides by doing 10 to the left and 10 to the right, works just as well. But in the case where they're both logs of the same, you can just eliminate the middleman. So x squared plus 3x equals 10. Quadratics, we love to be equal to 0. Factors of negative 10 that add up to be positive 3 would, of course, be plus 5 and minus 2. That potentially means that negative 5 and 2 could be solutions. If you go back, remember always to the original. Looks like the 2 checks out fine, where the negative 5 does not. So 2 would be your only solution. And last but not least, number 6. So remember algebra first. I'm going to go ahead and add the 3. So ln of 2x minus 1 is going to be equal to 2. Because of the fact that this is a natural log, I'm going to exponentiate using base e. So e to the left side equals e to the right side. Using that inverse rule, e to the ln base e cancels to be 2x minus 1, where e squared, we're just going to leave it. To get the x all by itself, you would take e squared and add 1, and then ultimately divided by 2. That would be your exact answer, which if you were to find the equivalent decimal would be 4.195. So in tonight's homework, number 36, you're going to see a mix of exponential and log equations. So you have to make sure that you can solve either type of either equation using the best and most efficient method. So thanks very much for tuning in, guys, and we will catch you next time.